So as I mentioned in the first video in chapter 10, gases are interesting because they have these interesting physical properties, and I mentioned that those properties are really defined by these key variables: pressure, volume, temperature, and N being the amount or the quantity or moles of a particular gas. The relationship, the quantitative relationship and qualitative relationship between these variables on the physical properties of the gas are related through these things called gas laws. And so we'll walk through several of the gas laws, though the gas laws themselves aren't super important. What's more important is the relationships that are established between these variables, and ultimately the final relationship between all of the variables, which will derive as the ideal gas law. So the first of the few gas laws we'll talk about is this one called Boyle's law, which again, I don't care if you remember the person's name. It's the relationship that's important. And Boyle's law was the first to relate the proportionality between pressure and volume. So let me show you a quick demo that I would normally do in class that illustrates this, and let's think this through together. So in the video, I won't show you the preparation for all these things, but what's going to happen is this person's going to have a can of an aluminum can of, say, Coca-Cola, and they're going to add to that can just a really thin layer, maybe 10 or 20 milliliters of water down in the bottom. They're going to put it on a stove, and they're going to heat that up until they start to see a little bit of water vapor leaving through the top of the Coke can. What they'll do then is have a dish set up just adjacent to that with ice water inside of it, and they're going to take this whole can and they're going to invert it upside down in this ice water bath. And the question I want you to think about is, based on your intuition here, what's going to happen? You've got this can that's got essentially boiling water, just a little bit, and a bunch of air, and you've heated it up considerably, enough so that you start to have water vapor leaving, and there's one opening right here on the top of the can. So then you invert it, and the opening is now down here, and this hot can is now being submerged in the ice water. What do you think is going to happen? All right, so let's watch a quick YouTube demo of this, and let's see if your hypothesis fits what actually happens experimentally.
Can into the water.
So let's try to rationalize what just happened in that video. So as you saw, the can imploded on itself, so it crushed itself and folded in like this. So what do we know about what was happening in this can? Well, let's sort of break it down. In the can, to start with, you've got this water vapor, and you start to take liquid water and you're converting that into gas vapor, which means you're putting more gas into this can, which is pushing outward on the can itself, right? There's some pressure being exerted outward on the can. And then when you invert it and you seal the top off, essentially, and you cool that water, so you've got a bunch of vapor water in here that's pushing the can outward, right? The force is outward in all directions inside of this can because of these water vapor molecules that are colliding with the walls. But then you rapidly cool the can, and what happens to those gaseous molecules of water that are in the can? They're in like this. What happens to those water molecules? Well, they very rapidly recondense back into liquid water because the temperature now is below the boiling point of water. And so now what happens to the pressure that's pushing outward on the interior of the can? Well, it collapses, right? There's a lot less pressure inside the can at that moment, and the pressure in the can is less than that of the atmospheric pressure that's pushing inward. And so since it's a sealed system and you just recondensed all of the liquid water and there's nothing pushing outward anymore in here, now the pressure of the atmosphere is greater than the pressure inside the can, and so you get this thing to collapse on itself. So what does that tell us about the relationship between pressure and volume, which is essentially what Boyle's law is getting at? Well, if we think about it in terms of this container over here on the left, if we have a volume of gas inside this chamber, this is the green stuff, and that's sitting at a liter of this stuff, and we start to exert a pressure on this, at equilibrium, we'll achieve some sort of volume. We'll just assume this is the volume that we achieve. So at atmospheric pressure, the volume in this canister is a liter. But what happens if we have a piston on this thing and we can push down at double the pressure as before? What does your intuition say about this relationship? Well, hopefully your intuition says that because gases are compressible, as we increase the pressure, so as pressure goes up, volume goes down in an equal and opposite way. And so we can write that in terms of its algebraic relationship. We could say that pressure is proportional, and I'm going to use this little, it looks like an alpha sign, but this is the sign for proportionality. So it's proportional to 1 over volume, meaning they have an inverse relationship. As you increase the pressure by double, the volume decreases by double, or by half in that case. So Boyle's law, and I should state that this is assuming two things. This is assuming constant temp and constant amount of stuff, meaning whatever the number of molecules of gas in here isn't changing, and the temperature of the gas isn't changing in either. So the only variables that are changing are pressure and volume, and what we see is this relationship that establishes an inverse quality between pressure and the volume of a gas. So what would that look like if we made a plot of volume versus pressure like this? Well, we'd say that as if we started with a volume here and a pressure down here, low pressure, and we started to ramp up the pressure in this direction, we'd expect this to have this sort of hyperbolic type of relationship that goes as 1 over v. So the volume goes as 1 over v relative to p. If we wanted to plot this directly then in a linear way, or linearize this expression, what we could do is plot this as volume versus 1 over p, and that would establish a direct, nice linear relationship between the two, and we would have then a slope of the line that would be proportional to some constant, right? Some constant that relates these two things together. And so that constant is the constant of proportionality, which we could write this equation out as V equals K times 1 over P plus 0. This being the equation of a straight line. Remember from high school algebra that this takes on this y equals mx plus b relationship, where y in this case is v, right? It's on the y-axis. X in this case is 1 over p because it's on the x-axis. The slope of relating these two variables together is going to be m, which in this case is just some constant of proportionality, and the intercept here, b, goes through 0. So our overall relationship here for Boyle's law was stating that essentially volume is equal to K over P, where this is some constant of proportionality. And this is how all scientific expressions are created. Some relationship is established between the two known variables, and then the constant of proportionality is used to adjust the units and make sure the units are sound. So in other words, Boyle's law could be simplified as P times V is equal to some constant of proportionality. That's the relationship. Boyle's law is as P goes up, V goes down in an equal and opposite way, and they're related through some constant K, which is unimportant in this relationship. It's just a constant. So Charles' law, the second law that we want to think about, relates the two variables volume and temperature. So how is the volume of a gas impacted by the temperature? And I think you have probably a pretty good intuition of this as well. So what I'm showing you here is the vessel. We've got, again, this is assuming constant N and constant P in this case. So whatever variables are not being related, we're assuming the others are to be constant. So we've got a half a liter of something with a pressure of 1 atm pushing down, and this is at 200 Kelvin, so pretty cold, knowing that 298, again, 298 Kelvin is roughly 25 C, that's roughly room temp, so pretty cold. If we start to heat this vessel up, what do we expect to happen between the space that exists between gas molecules? Well, hopefully you'd start to think that the gas molecules, because temperature is a proxy for heat, which is really a measure of molecular motion, that as you add more heat to the system or increase its temperature, these things are going to start running into each other more and more, which means they're going to separate more and more. They're going to get further and further apart. If they get further and further apart, that means the volume is going to go up. So as we heat the system up, in this case we double the temperature, what happens to the volume? It also doubles. And so in Charles' law, Charles is saying that the volume of a gas is directly proportional to its temperature. So we can do the same exercise that we did before, where we plot volume and temperature. This time these things are linearly related directly through each other. And through the same sort of y equals mx plus b procedure, the slope of this line is going to equal some constant of proportionality, k. And so we could write up an expression that says v equals k times t plus, again, the 0 y-intercept. Again, we're relating this to y equals mx plus b. So this would be y, this would be x, and m here is k. So we could think about or rewrite this expression as v over t equals k. Or in other words, as the temperature goes up, then the volume goes up in a linear relationship, in a one-to-one, based on this expression. That's what Charles' law would state. All right, the third and final law we'll talk about here is Avogadro's law. Again, I don't care if you remember the name, just think about the qualitative relationship here. So it's thinking about the relationship between the volume of a gas and the amount or the number of moles of a gas. Again, pretty intuitive. So if we look at the sort of graphic here, we can see that if we've got a mole of substance to start with, and again, we're assuming constant pressure and temperature in this case. So pressure is an atmosphere in both cases, temperature is constant in both cases. If we've got a mole of this gas under these standard conditions, that's going to equate to 22.4 liters of the gas. If we double the number of moles, we double the volume. And hopefully that makes intuitive sense. This 22.4 is not a unique number. This is actually a number that is useful to us because it states that under standard temperature and pressure conditions, then the volume of 1 mole of a gas is going to be 22.4 liters, and that's always going to be true. So that's for 1 mole of gas. I'll also state that these thermodynamic standard state conditions that we talked about before are slightly different for gases than they are for the solutions that we were referring to in the thermochem chapter, which is a little annoying. But the temperature here is 0 degrees C, which is instead of 25 degrees C that we talked about in STP for thermochem. Everything else is still the same, so pressure is 1 atm, and N in this case is 1 mole. So if you're thinking about standard conditions for a gas, we're talking about 0 C, 1 atm, 1 mole of stuff instead of 25. But the interesting implication is then 1 mole of gas regardless of the identity of the gas. It could be CH4, it could be neon, it could be ethylene gas. Doesn't matter what they are. If it's at 0 degrees, 1 atm, and there's 1 mole of it, then the volume of the container of which it will fill will all be the same. So that's the interesting properties of gases, which we don't have with liquids and solids, where the densities of those things are different, in which case the volumes would be different as a function of temperature.